Okay, good afternoon, everyone. Please welcome to our event IEEE Distinguished Lecture. Introducing, my name is Muhammad Ilham Azetra, but you can call me Ilham. I'm honored to be your MC today in this special event. With our guest is Professor Swadesde. Please welcome to our event IEEE Distinguished Lecture. Introducing, my name is Muhammad Ilham Azetra, but you can call me Ilham. I'm honored to be your MC today in this special event. Sorry for the trouble. Today's topic is there's only two. First is AML-aided sustainable IoT for smart environments, and also the second topic is intelligent task offloading in edge-assisted UAV surveillance. We are privileged to have this distinguished speaker with us, Prof. Swadesde. Thank you for your coming to Bandung. And I'm sure today's talk will be insightful for everyone here. Thank you for coming to our event. Before we begin, let us hear a few opening words from the chair of IEEE event, Professor Endra Julianto. For Professor Endra Julianto, please talk.
First of all, I would like to welcome Prof. Swadesde from Indian Institute of Technology, Delhi. And he is the IEEE Distinguished Lecturer from IEEE Communication Society, and the other one from IEEE Vehicular Technology Society. And one of the requirements for IEEE Distinguished Lecture is to give a lecture. Especially in this case, he gives lecture in 3 cities. So this is a 3 cities lecture in Indonesia. Yesterday, he was in Udayana, Bali, giving the first lecture. And then after that, he go to Bandung this morning, just arrived. To give the second lecture in the Department of Engineering Physics, Faculty of Industrial Technology, Institute of Technology Bandung, and also collaborated with the School of Electrical Engineering, Institute of Technology Bandung. And then tomorrow, he will go to University Indonesia to give the third lecture. And after that, I think you will go back to Bali again? And then go back to India. So you know there's a very big effort for Professor Swadesde to come to Indonesia and to give lecture in 3 cities. And this is very lucky for us that it is a good opportunity that he will share his research achievement, and also that what is the experiment that he has been done to achieve that achievement, especially as an IEEE Distinguished Lecturer. And to short the introduction, I like to finish my introduction here, and then I would like to give to the to the MC, and then give the Professor Swadesde the lecture time. Thank you.
Okay, thank you for Professor Endra for the opening remarks. Okay, let's on. We come to the main session for our event. Please welcome Professor Swadesde, our distinguished speaker, who will deliver this lecture and will be moderated by Professor Endra Julianto. For the floor is yours, Professor.
Thank you, Professor Endra, for inviting me, and this is an opportunity for me to visit this exotic country. So I always like traveling to new places. So that's an opportunity I took, and then Professor Endra and other colleagues helped in this. And with regard to my talk today, so this is, I have been doing research in broadly wireless networks and resource allocation, resource optimization, energy efficiency, green communication, sustainable communication. These are the keywords. But with that keyword or with these thoughts in mind, I have taken different directions actually. So one of the directions that we are going to discuss is one of them. Actually, that takes me to a direction which actually by itself is unique. That IoT. Sometimes people say that okay, I am IoT expert, but I feel this is not complete actually. IoT is only a small part of it. But the bottom line is that we are not doing IoT research as such. So IoT means it is kind of perceived as having some building block connected and then making things work. This is not we are doing at all here actually. So here this talk is about smart IoT. Again, by smart IoT or smart connectivity, people normally mean that connectivity aspect. Smart IoT means that okay, it will connect from, let's say, one network fails, another network takes over, etc. So this terminology again may not be appropriate, but we are talking about how to impart intelligence into the devices. Again, this is a buzzword worldwide, but again, I have found my buzzword organically, and that is what I would like to explain. And hopefully this will motivate how the problem definitions came one from another to another and so on actually. So this is one takeaway for the students. And the topic chosen for this today's talk is interesting in the sense that this possibly is good for particularly the students who are beginners or who are testing themselves. What is research? Why people do research? So I think this could be interesting. I hope you will find some threads of such aspects actually. Okay. So I think is this possible to have a pointer, not pointer, but slide changer, because it is rather difficult for me to ask you to go back and forth because you don't have pointer. Okay. So in that case, can you place this over here, computer? I'll do the changes. Just rotate it a little bit. This would be, yeah, this would be okay. Maybe I'll stand here. That is okay. So
It's already.
right. Okay. Yeah. So there are actually the number of slides are too many for let's say 1 hour talk. It is a lot many actually. So what I will do is, so the other part of the topic is reasonably different. I will try to give a glimpse of that, but let us try to get to this and see how much we can go through actually. So there are multiple. So what we are. So in fact, if you have noticed that I have changed the title a little bit. Data-driven optimization and lightweight ML aided smart IoT. And again, the smart environment question is that everything that we are doing is actually energy optimization, green communication, and there are certain aspects actually. So as such, I am not working on environmental research. So the focus is that if we make them energy sustainable, that itself helps in environment. That's how we can look at actually. So what we quickly go to the next. So basically the Internet of Things. This is I think almost all of you would appreciate this slide as such. This today the buzzword is that we want everything to be networked. Okay. So even my so let's say a soldier's uniform is also having these sensors, and these sensors are monitoring not only health parameters of that soldier and all maybe other some things, and these are also passing that information to the outside cloud, and so that the person's health and environment is monitored accordingly actually. So this is a smart everything. So this is actually a smart environment if you call it actually. But here we are talking about, so smart environment is from that aspect. What we are talking about smartness is about how to impart the additional capabilities so that to achieve this smart environment we consume least amount of resources. It could be energy resource, it could be bandwidth resource, processing resource, etc. Okay. So at any point in time, if you have any question, feel free to ask. Because I have not slept well last night, I might feel sleepy also. If you ask question, then I will know that okay, I am in tune with you. Okay, it will help me also to be motivated. Okay, please feel free to ask question. Okay, so first few slides are very basic actually, in the sense that, so this is from networks perspective. What we do, we want to study the network performance. So network performance, certain parameters could be, these are example, congestion, delay, blocked call, dropped call, quality of service, quality of experience. So if you classify, we first talk about SNR is one pure physical layer. People want to restrict themselves as SNR. As long as I maintain the SNR, as if everything is done, which is not the true thing. Then one level next is that bit error rate. Then comes bit error rate does not necessarily guarantee. In fact, SNR doesn't necessarily guarantee bit error rate. It's not one-to-one correspondence. And then likewise, bit error rate does not have one-to-one corresponds to packet error rate. Packet error rate does not necessarily correspond to QoS. QoS is a more composite term. Quality of service actually is subjective depending on the application. And then quality of experience is another subjective actually. I can keep on giving example why this, let's say, your quality of service is not necessarily quality of experience. Okay, so but question is that these are certain parameters that we are well aware already, and in all cases concerns of resource efficiency. So for that, what we have is that we start doing, let's say, from the network planning perspective, we do optimization, let's say, routing, what should be the routing, what should be the switching, etc. And also from resource management perspective, meaning that so basically these optimizations are done at kind of two stages. One is at the deployment stage or before your deployment stage, and another is when the network is deployed, you need to optimize. That optimization is because at the deployment stage, when you did some computation calculation, these computations made some assumptions. These assumptions are not necessarily reality. Real life situation is very different from the assumptions that we make in analysis. Actually, I will come to the next slide and it will. So basically, modeling and analysis are the keywords to capture these aspects actually. Now, so this is what now modeling and analysis involves. Let's say there are three classical ways to do: measurement-based, simulation-based, analytical. So analytical is what I was talking about. That when I don't have anything. Let's say I'm trying to develop a network. I don't have anything, so I have to make assumptions, to make some analysis, to make a prediction or kind of estimation. So this is a system level understanding is required, of course, but mathematical skills are majorly required, and merits are that it is least effortsome in the sense that if I have mathematical skill, nothing else is required. Okay. Communication theory people are of such kind of people actually. They don't require anything else because they are mathematically very skillful and they can maneuver. But what they have to do is they have to make assumptions, and their assumptions actually take away the problem from reality. Okay, so that is what we mentioned in the last bullet actually. So this is other advantages are mentioned, least accurate because of the assumptions and so on. On the other extreme is the measurement based. So instrumentation required, experimental hardware required, which is many cases not possible because of cost, because of convenience, and so on. And also these experimentation is difficult to, as the what is that called, technology changes, same experimentation doesn't work. You have to upgrade yourselves actually. So expensive, time consuming. Many a times students don't want to take up experimental research because setting up these experimental setup itself is too much time consuming. Cost, I mentioned already, non-repetitive measurements. For example, I say, okay, with these components I have done these things. Now a reviewer gets this paper, he says, okay, I don't know whether it is verifiable or not, because it doesn't have, but still I have confidence, I have done these things, but it is that way the challenging actually. Analysis has that advantage, mathematics is a universal language. And not compatible with future design, understandable, and simulation is in between. Again, I am not going to spend much time here. So in between, in the sense that pure simulation is not acceptable because we do not know whether we made knowingly error or unknowingly error, and sometimes this is in between actually. So in all these cases, performance modeling and analysis, if we talk about, we are going to focus on the some analytical tool. In our case, network performance analysis, one tool that is of majorly heavily utilized is stochastic processes, knowledge of stochastic processes. So definition I am not going to go through. So again, this slide is also not required. So basically, this is a kind of a more for tutorial. I am not going to spend time actually. So Markov here, stochastic process can be characterized if I have certain parameters. Let's spend time on that actually. So if I go back to this slide here, so this is based on certain assumption that the process that I am dealing with is wide sense stationary. Okay, WSS process. Okay, and if I have why so there is a difference between stationarity and wide sense stationarity. The students are aware of that. Stationarity is too constrained, and we don't require to deal with that because we don't require anything beyond second moment. Today's analysis, we restrict ourselves to the up to second moment. So as long as the process is WSS, this is fine. But this is what we are talking about. Stationarity of the process is assumed, which may not be true in real life. And mathematical model thus obtained is only an approximate representation of the process. So, and that is where we tend to do something which is data driven. Okay, data driven, adaptive, adaptive to the dynamics of real world, and it is robust but computationally intensive. So, and today's technology, today we are actually picking up that data driven approach more and more because computation resources are actually too many today, and we are not actually constrained by computation resource as a result. And also data generation is also easy. Capturing data is easy. In fact, I will give some examples as we go actually. So next couple of slides are also kind of tutorial, but I will go through quickly for the benefit of the students. So why this is important? So you see this stochastic process and these stationarity, these concepts are well known actually. Dynamic stochastic process is already very well known actually. We used to live with it so far, as I mentioned, because optimization used to be not so critical actually. So that is, these are the certain points beyond classical communication, pervasiveness of wireless communication applications. So today, as we were showing in the one of the slides, that we want to have everything connected. So everything connected, and yesterday only in the conference, people were talking about smart agriculture. You give a proof of concept, but it is not scalable. What is the problem? Problem is that you cannot go and recharge your thousands of nodes. And you cannot redeploy because cost. So cost is heavily important, energy optimization is heavily important, and also energy sustainability is important. So that then only. So this question is coming because we are talking about, today we are talking about pervasive communication. So this has started from 5G. Okay, up to 4G we were talking about only rate increase and so on. 5G has started that, okay, everything connected, everything connected, network of everything actually. And 6G is actually, 5G started the buzzword, but it did not do much on optimization actually. And in 6G it is picking up further actually. So, so pervasiveness is the key word. And other thing is that because we are talking about everything connected, so the end entity is having some capability, its connectivity is of different type. It goes to next, let's say edge is connectivity of different type, and then it goes to, let's say, core network different. So because of the so many different technologies, it is difficult to have an end-to-end analysis using theoretical tool. It is rather easier to, if some deployment has happened, you start collecting data and then start understand the behavior and then start optimizing. This is much easier actually. So this is also a natural motivation. And personalization, this is in fact that is what I was talking about QoS and QoE question actually, leveraging the user behavior. So my requirement actually changes with my situation actually. So if I am in office, my expectation, let's say I am watching a video, expectation on the video quality would be something compared to when I am on the move. Let's say I am driving car and yet I want to watch a cricket match. My expectation is going to be different because my focus is not there actually. My device is smaller. My resolution is this thing. And also I want to save more energy because my device has to sustain possibly next 3 hours that I'll be on the road actually. So the personalization is very related, connected with many other things actually. It changes time to time, same person's behavior changes and so on actually. So now need for data. So this is need for data driven and AI/ML strategies. This is AI integration. So signal processing tools can be quickly enhanced by looking at the data dynamics actually. So signal processing you can do, as I mentioned, considering the stationarity assumption. But because it is not stationary, it could be actually easier to look at the data. Let's say you capture certain data and then based on that immediate past history, you design your optimization, signal processing optimization. So it is again data driven, it becomes actually. And then fine, I think. And ML algorithms employing neural network, I think this is not much. And resource optimization, ensuring efficient utilization of limited spectrum from another aspect actually. So this is an example of spectrum optimization, but energy resources through intelligent algorithm. Now why now? This question I have already addressed. This beyond 5G, addressing critical need for intelligent solutions in the era of 5G and implementing 6G, characterized by URLLC and MMTC. So data explosion, I mentioned that there are the data availability is easy today, and then it makes our life easy to actually go by data driven approach actually. Okay, so this is again for just possibly I don't need to spend time actually. So the AI ML techniques, again I am not AI ML expert as such, I am user of AI ML only, but the idea is that these AI ML concept theory has been developed in 1960s, and today in the let's say 2020s and IoT era, AI at the edge, this is actually flourishing today actually. The evolution is what we are talking about. And everywhere we are talking about using AI, and this is, so the one thing that I also wanted to carry here is that we are trying to use AI not because AI is hot, but because we are motivating ourselves that because of certain constraint we need to use AI to improve the performance actually. So dynamically adaptive system would be more efficient with respect to everything, and the dynamic adaptation is going to be offered by the learning the history. And learning history could be based on pure data, then I call pure ML. If it is based on some multiple other history, then I call AI. Okay, AI is actually a deep learning, that is all. Deep learning term has been now modified as AI anyways. So with that, this module was not my original agenda, but when I was thinking about presenting this, I thought this module is actually of very interesting, useful. So I wanted to present actually. So this for this I will first go through this. My slides are not organized very well here. I will go to this slide first here. So what we were doing, this was one of our work possibly about 10 years ago. So we were proposing a we call energy efficient dynamic spectrum access technique. So energy efficient dynamic spectrum access algorithm we wanted to develop. So the assumption we are making for that problem formulation is that I am given one channel, and that channel is used by certain users, primary users we call, and secondary users want to use that channel as and when it is available. Okay, so that availability can be imagined that like this actually. So this green portion means channel is available and red portion means channel is not available. Okay, and this continues. Now I am a secondary user, let's say. My job is to assess as accurately as possible beginning of the green channel, green moment, and then assessment also has to be, if the assessment is accurate, then I can actually assess possibly almost accurately this much time, so I can utilize efficiently. If my assessment is wrong, for example, if I, let's say, tap at this point and find channel is green, means channel is available, and I do not know how long it is going to be available, then I will possibly utilize this much time, then I have to sense again, and I find channel is available again, and so on. So our motivation was that to develop an algorithm, energy efficient algorithm, to ensure that my sensing is not unnecessary, and yet I am able to predict the channel availability and unavailability as good as possible. Okay, so that was the motivation. So to do that, so this thing can be modeled as an on-off process. Okay, on-off process. Okay, channel is on, channel is off. Okay, so a traffic arrival process has been modeled as on-off process. Here we are modeling the basically channel availability or unavailability as on-off process. That is fine. Now I am interested in utilizing the channel when channel is off. Off means there is no primary customer using the channel, right? So how to model? That is where when we are formulating the problem, we found that problem has lot of deeper intricacy, and we wanted to have a simplifying assumption. What is that assumption? We made an assumption that on duration is exponentially distributed and off duration is also exponentially distributed, but independently. Okay, so that assumption is reasonable in the sense that this is random. Okay, how long the channel is going to be available is actually random variable. That random variable we are saying this is exponentially distributed. Off duration is also a random variable. We are approximating this as exponentially distributed. We chose exponential distribution. Why? Because exponential distribution is memoryless distribution, and we can actually have a tractable formulation to start with. Problem has its own intricacy later, so we made that assumption. So we made the assumption, we did some work, and this paper was published in 2016, Transactional Mobile Computing, which is a good place. But we were also questioning ourselves how good the assumption is. Okay, and that led us to a data-driven work actually. So what we did, when we were working, we thought, okay, let us do some experiment, do some study about actual packet arrival process. Okay, we created an experimental setup. Okay, this one. So we created an experimental setup that I have a Skype communication. So there is in the network, in our lab, we turned off nearby all access points, and then we used our own access point for this purpose, and through that access point we set up a Skype connectivity. It goes through the access point, it goes to the internet world, and it goes to the other party. Maybe a student set up a connection from the lab to his friend somewhere. Okay, and we use software defined radio to capture this traffic. As the wireless communication is happening, the packets are going and coming, two-way communication. This SDR is capturing the channel availability and unavailability. Basically, there is a tool called WireShark, packet traffic sniffer. Using WireShark, where channel is available, this energy level is high, low, and so on. When channel is available, energy detected is low, and when channel is unavailable, energy detected is high, and correspondingly, how long this energy detected is high is considered there is a packet transmitted. Okay, so using WireShark, using SDR, and in the background using WireShark, we were able to capture the Skype packet arrival. Likewise, we tried with this thing. Likewise, we also went to a generic environment in our we call wind tunnel, where lots of students are sitting there around doing experiments, doing their own work, chatting, etc. We captured this traffic, and using this captured traffic, now we wanted to study this on duration and off duration. Very simple experiment actually. So we first job is to capture this traffic using this WireShark, and then we wanted to see the distribution. So again, this is now for the students. This is actually a class problem. This work was done by an MTech student actually. It was his MTech project actually. So Question is that if I give you a bunch of random variables, using that you are asked to find out the distribution of the random numbers. You can do that, right? Those who have studied random process, random variables, you might have studied that actually. I give you a bunch of numbers which are random, okay? And I am asking you to find out the distribution of the random number. It is possible, very easily possible. Basically, you can do a simple bin, let's say, depending on the granularity, depending on the range of the variable, you can define some granularity that you can point between this and this size, how many times I got this packet, how many times I got this packet of this size, and so on. Using that, you can find out, this is an easy problem. If you have not done that, you take that problem today actually. Okay, so you generate some random number. You see your MATLAB, your computer generates uniform distributed random number. Okay, but how do you know that is uniform distributed? Prove yourself. Okay, you generate random numbers using the computer generated number, and then you plot this, capture this data, and then plot the distribution. You will actually see. Okay, so this is easy. This is actually empirical study. This is easy actually. Okay, so this is the second task. First task is the capturing data. Second task is to generate the distribution, empirical distribution. So that empirical distribution, this is the energy captured actually. I will go to the empirical distribution. The empirical distribution of the busy period and idle period are looking like this. Okay, this is empirically collected from the collected data actually. So now go back and think of what our assumption. Our assumption was that this is the busy period, means on duration, and idle period means off duration. We assume that on duration is exponentially distributed, something like that. Off duration is exponentially distributed, something like that. But this is far from that assumption. Okay, that actually shows how badly we were doing in terms of our assumption actually. Okay, we did some theory, we did publication, but this assumption is, so that is the third part actually. We prove that our assumption is actually far away from actual distribution actually. Okay, so then the next question is that how do I make use of this outcome, that this distribution is looking to be very different, but I need to know the distribution. So, and if I know the distribution, I can utilize that. Now I may not be able to find a closed form expression for performance, but at least I can do using optimization. Okay, there is mathematical closed form expression will not happen, but I will use that distribution to predict actually. This distribution is required for prediction purpose only, right? So next question is that how do I model this distribution? This is another question which is already well known in theory. Maybe you have not done, maybe some of you have done, but this well known theory that we have used now. So from this distribution, what we find is that these look to be very picky. Okay, have you seen anyone who has done this probability theory? Have you seen such distribution? No, right? You have seen some continuous distribution, maybe Poisson, maybe Gaussian, maybe exponential, or maybe some discrete distribution, probability mass function. But probability mass functions are delta functions, right? But this is neither continuous nor delta function. Okay, there are some picky nature. So this is actually as if there is a Gaussian here, as if there is a Gaussian here, there is a small Gaussian here, there is a Gaussian here, and so on actually. So this is called sum of Gaussians. Okay, this is actually sum of Gaussians actually. So and this distribution is called Gaussian mixture distribution. So this is what we did. By intuition, by looking at this thing, we felt that this is sum of Gaussian. Now let us do this modeling using Gaussian mixture modeling. So GMM is actually a well-known theory in the literature, and in your image processing community use heavily this one. Here our GMM requirement is actually one-dimensional. They do two-dimensional, three-dimensional because they deal with two-dimensional, three-dimensional data. So we did basically GMM. Okay, and then we did some interesting optimization there, that we do not need to go by the classical expectation maximization algorithm. We actually reduced this thing based on, that is our research contribution, additional research contribution. So now the distribution theoretically looks like this. Okay, so the distribution has up to k such components, Gaussian components, and each component has certain mean, certain variance, and certain weight. Okay, going back to that, as if the first distribution has a higher weight, second distribution has a little lower weight, and if I ignore for now, this distribution has another little lower weight, and so on. So these are corresponding WJs, and these weights are correspondingly sigma j's, and where it is happening, this correspondingly mu j's actually. So we need to run this algorithm until we match this empirical distribution close to the model distribution. Okay, so this is actually, as I mentioned, this is known theory. This GMM modeling, there are two steps. One is called k-means clustering, another is expectation maximization. So we choose the value of k. If I don't know anything, I start with k equal to 1, and then I try to find corresponding w, corresponding sigma, and corresponding mu, and I try to find out some distribution, and that distribution I'll see what is the closeness of the model distribution with respect to the empirical distribution. Closeness is the distance between two distributions, and there are a lot of information theoretic distances. We used for our work currently, we used some K's distance, Kolmogorov-Smirnov distance measure. So this is the algorithm. There are some optimization here compared to the algorithm that was given here. So we use this thing. Basically, this is my model distribution, and this is the modeled CDF, and this is the empirical CDF, and we are looking at this distance. This distance, if the distance is large, we call that this modeling is not good enough, and we try to minimize the distance as we go. And if we continue to increase k equal to 2, 3, 4 up to infinity, it has to match very, very closely to the empirical distribution. In fact, any distribution can be modeled using Gaussian mixture, but the challenge is that if I have the continuous distribution, if I try to model, I need to have infinite values, number of k's, which is computationally exponentially intensive. It is not possible feasibly. In our case, because this is peaky distribution, I don't need to go into. In fact, some results are showing further actually. So this shows here that we have this is the original this CDF. CDF is comparison is what we are doing. This is the empirical CDF, and then if I do hyper exponential, some other people proposed earlier, exponential we proposed, generalized Pareto another researchers proposed, and then we consider 3 Gaussian mixture, 4 Gaussian mixture, 5 Gaussian mixture, and we see at some point this is matching. This is not very clearly visible. This is more easily visible, that 5 mixture is almost matching, but we have some numbers also here. It says that as I grow from 1 GM to 2 GM to 3 GM to 4 GM, 5 GM, you see 4 GM to 5 GM, no change here. Change is now diminished. Change is a little bit, change is reducing actually. So something as you go here, this to this. So as I mentioned, we can keep on doing these things, and we choose to stop wherever we feel the distance is acceptable. Okay, this is how. So we could model this empirical distribution with an equation actually. So that equation is actually important for us, because that equation will be used for our prediction purpose. This is now a as if known distribution. Known distribution was exponential, instead this actually. So this is the fourth component of that work actually. And finally, we tested this algorithm with some other to study the performance of the protocol that we originally proposed. So we called energy efficient dynamic spectrum access. So energy efficient dynamic spectrum access, if I do exponential assumption, exponential distributed on and off duration, where it goes in terms of good put, in terms of energy efficiency. Good put is about how well I am utilizing the channel, and energy efficiency is about how much I am wasting my energy in sensing the channel unnecessarily. Okay, it shows some benefit, and likewise there is some another comparison. I am quickly go. What happened? Yeah. So this is another comparison with another paper actually. So it shows that different observations. So as I mentioned, intuitively we have this Gaussian mixture cannot be beaten by anyone, because that is empirically observed and modeled using Gaussian mixture. So this is doing this much better actually. Okay, so this actually gave a very clean paper, as you can see here. This but there are twofold challenges here actually. One is that as we why we wanted to do that, we wanted to actually remember we are interested in doing this exercise for making the prediction about the channel on real time basis actually. Now what happened is that as we are capturing the data and then trying to do the channel estimate, this process is very time consuming, process consuming actually, computationally intensive actually. So I have to capture this data, I have to correspondingly assess what is, so this is channel availability on duration and off duration are on the order of milliseconds, maybe 2-3 milliseconds or so. Whereas my processing time takes maybe more than maybe tens of seconds actually. Now I can use higher end processors, possibly it can be reduced a little bit, but still it is a problem. So actual real life implementation is a question. In fact, we cannot use, our coding was MATLAB based here, this SDR coding was MATLAB based, but so although we were able to predict, and we are basically assuming that if I am able to predict, then we can utilize this and this much. But that prediction on real time is a challenge, and that challenge we actually did not tackle for real implementation. So that real implementation has to be done possibly using FPGA so that these delay concerns can be taken care. The other challenge is that, remember that we have started with some Wi-Fi access network. In that scenario, the packet distribution is something. This same equation, the model that I have used, the same model will not be applicable in, let's say, cellular scenario, because cellular data traffic is something else. This same model may not work in the weekends. Okay, so what I have to do is that I have to have the data-driven engines continually operating, where depending on the environment, depending on the time of the day, depending on the season, it has to continually update itself and then predict, come up with that modified Gaussian mixture model. So that is the overhead actually we are introducing, but with the purpose that we are going to achieve some benefit actually. So in summary, one can actually look at this exercise, do this exercise for other bands and other applications also. Okay, so that is that kind of the data-driven optimization term I introduced with that thought actually, and also that helps me to introduce one concept of Gaussian mixture model, which is we are going to use in the subsequent works actually. So this module, second module, is actually actually took me from my conventional research altogether. So this is, I was called by some power systems colleagues for writing a proposal that they are interested in writing a joint collaboration proposal for smart grid infrastructure development. So for me, my task was that they are interested in smart grid infrastructure development, where there will be some smart grid health monitoring gadgets, which are called PMUs, phasor measurement units, and from the communication perspective, we can call them real-time IoT devices. Okay, so these are certain IoT devices which are like here. This is an IoT device which is attached, let's say, along this at this junction, and this is another IoT device, and so on. These IoT devices. So my task given to me was that what is the optimal number of IoT device, such PMUs required to be deployed? What is the network capacity to be designed, and so on actually. So and network connectivity, network resources, these are the tasks given actually. So I wanted to, because here these data communication, basically network health parameters are being collected by these IoT devices or PMUs. These PMUs are going to generate some data, and then these data, for that data I need to have sufficient network infrastructure so that it can handle actually. So I went back, I thought, okay, let me first understand the device that we are talking about. The device here is the PMU. So what kind of data this PMU generates? So that was my simple question. And then we got to got hold of some power grid data that are collected. Today PMU is not used. This is actually next generation. These people are experimenting. Today their SCADA systems are used actually, and this but in any case, these the power grid health parameters that it collects are different frequencies, rate of change of frequency, different phasor current, phasor voltage, and etc. There are some 9 parameters, 9 useful parameters, and there are some other health parameters like temperature and other parameters actually. So we collected some such data from the what is that called, some synthetic data as well as the northern grid data in India actually. And out of these data, so there are not many details. These slides are a little bit cryptic here. So out of these, data, again, as a novice in this area, so we focused on one parameter which is called rate of change of frequency. So apparently in power grid health monitoring, the parameter that is most critical is the rate of change of frequency. So what is the frequency of operation here? 50 hertz, 60 hertz? Your 60 hertz. So 60 hertz, it is supposed to, your power line is supposed to operate at that frequency, but it is not important whether it is operating at 60 hertz or minus or 58 hertz. Maybe 2-3 hertz deviation is okay, but the more important part is that how fast it changes. So if it was 58, if in the next moment it goes to 60 or 61, that is much more dangerous. So rate of change of frequency, because rate of change of frequency, what is that called, proves or rather indicates the instability of the network, right? This is the control theoretic question actually. So basically how much of frequency you are generating and what is the oscillation actually, and what is, so that is a critical parameter. So rate of change of frequency is the most critical parameter, again by my colleagues given. So we thought, okay, let us study rate of change of frequency. So out of these multiple parameters, now I am focusing on one parameter, which is rate of change of frequency. I have a data series, and using the data series, I wanted to first see, I wanted to understand what to do with the data actually. So one thing, again, I have been told that these data are time critical data, because power grid health has to be monitored instantly, and then if some bad thing is happening, that has to be acted upon instantly. So real time communication actually, real time IoT. So we are looking at these. So now my objective as a applied stochastic person, looking at the data series and try to see what is the behavior nature of the data. Okay, so that was my starting point of thought actually. So again, I am not going to go through many things. We tried several things. We went very step by step actually. We started with, let us try to plot the distribution. Let us try to, I have a millions of, let's say, several days of data. So for one day data, using one day data, what is the distribution? Another day, is the distribution fitting? No. Next day it is not fitting. That means data is actually dynamic in nature actually. So dynamic in nature, that means I cannot go by my classical stochastic process. So that stationarity assumption that I was talking about, this cannot be done. Then the next question comes, so we tried many variants actually. In fact, there are papers also who have modeled this as ARMA process, and instead we wanted to look at further and then our, so yeah, I think I can also skip through. So going back to the diagram again, so this is called power distribution controller. So this is called, currently this is called power data collector actually. Controlling action is yet to be happening actually. So this is supposed to collect data from multiple directions. Now what to do with that? Currently this control is manual, but is supposed to be doing actuation by the PDC itself. So in any case, that has to be done on real-time basis. Whether it is done by machine or human, that is a second question. So, so the question is the stochasticity of the data. So one thing I was talking about the stationarity, and then other question is we are looking at the autocorrelation function, autocorrelation of the data. So as we have these data series, we have tried to plot the autocorrelation function. Autocorrelation function shows something interesting, that this is not what is that called. So again, so if I have a data series, and if so autocorrelation function, I think all of you are aware, right? Students, you have done at some point. So R tau. So basically, you are correlating with yourself at different points at time tau equal to 0 and at tau. So you are trying to find out what is the correlation, what is the similarity actually. Okay, similarity of this. So if the R tau is close to 0 for all other values other than tau equal to 0, then we call independent process. On the other hand, if the R tau is slowly varying, as you can see in this case, it is varying very slowly. Even if I am going from sample 0 to sample 2000, so it is very slowly varying actually. So if it is, so if we model the data to be completely uncorrelated, this should have been a delta function here, and rest it should have been 0 altogether. It is not. If it is exponential distributed, which is what we assume in our theoretical other studies, exponential distribution should be like this, and it will be saturating to 0 and going down as time progresses. In this case, what is happening, it is very slowly varying, and also it is kind of again anti-correlating and then coming back oscillating actually. So basically one thing that we observe from here is data is heavily correlated actually. In the literature, people say that if the correlation coefficient is above 0.5, this can be considered to be very predictable, okay, depending on the what is that called, quality of the prediction. So but as you can see, above 0.5 it is going up to 1000 samples actually. So data is heavily correlated, and that led us to think that, okay, why am I sending so much of data, this PMU that is manufactured and this is generating this much of huge data, why should I transmit all these data which are so heavily correlated? So that led us to think that let us try to look at if I can prune the content without losing the information. So that was the theme that we are talking about here actually. So how do I do that? Then the question is, so what we did, I have a single data stream, and what I am looking at now, I am not going to go through the theory much here. So there is a we have used support vector regression. There are other tools. We found this is most useful and easily manageable for us, because we are starting in that. So support vector regression. So what we are trying to do is that from the past few data up to, let's say, d values, this is called lag value, can I predict this Fi, current data? Fi is the current sample, and I am predicting this, which I am calling Fi hat. If Fi hat is close to Fi, then I declare Fi is redundant, because this is predictable from the past history actually. Okay, so then what I will do is I will my engine at the transmitter, at the data generator, I am actually creating a new engine actually. So earlier the data was being generated and dumped into the network. Now here I am saying I don't want to dump into the network, because network will be choked. I need to unnecessarily over design a network which is not required actually. Here what I want to do is I want to collect the data, and then individually actually, I am not actually processing in a batch. That is the key word again here. So once a sample comes, my engine immediately verifies whether the sample is predictable or not. If it is predictable, it simply drops the packet, and it continues to do that as long as it is able to predict within certain error margin. Error margin is in my control. I define, that's why it is called epsilon SVR. So epsilon, what is the error margin tolerable, that is in my control. I will within that I will predict, and as long as I am able to predict, I will continue to do that. So now what is that engine? That engine is the support vector machine actually. So this is actually a what is that called, supervised learning. I think students might be already aware of that. So supervised learning. So you have a data series, and from this data series you are training your machine. You are that machine parameters. In this case, what we are looking at, I think maybe here or somewhere else. This is the optimization, other details. I think, yeah. So we need to do these WAIs, phi function, and this what is that called? This is the bias. Okay, so these engines, certain parameters, again subvector machine study will give you that. So these need to be extracted from a set of what is that called, training data. I collected training data and then extract these machines parameters, and using these machines parameters I keep on predicting. As long as my prediction is within error bound, I continue to do that. The moment I see that my error is now exceeding, continuing to exceed, or maybe the error tendency of exceeding is higher, then I declare that my training has become obsolete. I have to retrain again. Okay, that is the simple thing that we are doing here actually. So at the source, I am doing that exercise. I have raw data. Raw data is being generated anyways. All I am doing is I am just using the raw data sometimes for retraining my system, and as I go continue, I am just sending nothing into the channel. So what is happening, instead of streaming the data into the network, I am sending very sporadically. Now when I am sending data, only when I am starting to train. When I am training, remember, when I am training, because I don't want to lose the integrity of the network, I am sending everything, because I have my machine has to be retrained. So during that time I will send everything that I have collected, so that I don't lose my data integrity. And once my training is done, I will again stop sending anything. That is the machines doing it. These details are about that actually. The length sequence is the training length, and so on. I think I'm skipping these things. So at the source we have this engine which is playing at the source, which is deciding not to train data, and at the receiver side, this is the PMU side, received sample from the PMU. It is trying to do the interpolation of the data actually. So what we are doing is that engine that I have trained at the source, that engine parameters I am passing to the other end. Using that parameter, it is trying to recreate those or estimate those parameters. This is again very standard actually. Okay, if there are questions, please raise. Now, so then we have certain ways to evaluate actually. So we need to ensure that by this process, in this process, we are not losing the data integrity. How do I verify? Disturbance index, meaning that how many times disturbance happened and yet I am not able to catch them actually. So that is one. Bandwidth saving, and so on. There are different parameters here. Disturbance index is mentioned. Measure of goodness of the model, identifying the fault scenarios or disturbance scenarios actually. Disturbance scenarios is where frequency change happens abruptly. Okay, so and some other parameters. Okay, your prediction ratio. Prediction ratio is to do with that. What is there any relation between the training length and the prediction length? Meaning that prediction length is that how long I don't have to transmit anything actually. So we basically played with what is the training. So when I am saying that I have to retrain my machine, how much data, background data is important? So that was the question we were talking about actually. So there are some observations here that these, as we were changing the lag value, so how many past history is important. So some in our particular scenario here, we got these lag value, certain lag value, up to certain lag value is going to be good. Beyond that, I am not getting anything. So it is rather. So basically, collecting more data for prediction purpose is not necessarily beneficial, and so on. I think what is going on here. So these are certain other results here, that how I am, so this is my actual data versus my predicted data, and the training, these where I have trained, and then this training continues here, this is a training, this is another training, and so on. So these are for different cases actually, different cases in the sense that in one case we are considering, this might be mentioned here, case 1 dynamic prediction model trained with actual frequency sample, and in this case based on the predicted frequency sample. There are many other internal details, but main crux I have mentioned already, that we are trying to do real-time data prediction and transfer, what is that called, we continue repeat the process of retraining as we go further. Okay, so again, please feel free to ask question. So here what we have seen is that performance wise we have bandwidth saving in different cases at different retraining count, how frequently I have to retrain, disturbance index. Disturbance index we have chosen to ensure that disturbance index does not go below 1, because that means I am actually losing predictability of the faulty scenarios, and so on. Okay, so this is I will skip through. So this corresponds to the error bound I was talking about, this epsilon. So if I have a crude error estimate, the error tolerance 0.1 hertz, then my bandwidth saving is much larger. On the other hand, if I say that this epsilon error bound has to be very tight, then corresponding energy saving, your bandwidth saving is actually lower, and so on, but still it gives certain benefit actually. So this is about this paper's particular direction, but what I wanted to do further here is, many other details are missing here actually. So what we did further in this exercise, there are many details missing here, which I think missed here, is that, so here we started with single parameter to, as I discussed here actually. Using single parameter, we made a case that I don't need to dump the entire data into the network. Instead, my machine at the PMU can be smarter. I can have a what is that called, a data processing module. That data processing module output will go to the network. So as a result, I am going to save a lot of radio interface energy as well as communication bandwidth and so on. Then next question that came to us is that now this looks to be easily implementable. We actually tried to do using Raspberry Pi, and then when we came across this thought that, okay, given that this PMU is generating multiple other parameters, I have two options. One is I can run this same engine for all the parameters, or I can look at all these parameters and then try to find if they are any ways related. Because all these parameters are collected from the same source, there might be possible that all these 8-9 parameters have some correlation actually. So exploiting the cross correlation, we tried to do the data processing, real-time data pruning for the entire all the streams now actually, all n streams that I am collecting, all n streams. So this is these details I have not included here actually. So that is one extension, that basically from single variate to multivariate. Again, for multivariate we played with different other options. LSTM was one of them, and we found out this multivariate SVM is doing well. What we found out is that, so out of these n streams, we do not need to deal with all the n streams. Rather, we created batches that, okay, out of these n streams, maybe there is one group who are somewhat interconnected. Out of them, we call one of them as the base attribute, and other are predictable attributes, secondary attributes. So I have to deal with only the base attribute. Likewise, another group, out of them I pick up only the base attribute. So now out of all these streams, I am dealing with only the base attributes, and on the base attributes individually we are applying the SVR. So that multivariate SVR. So that these we did not apply for patent, unfortunately, because we were not much aware at that time. That multivariate we patented, Indian and US patent. And the other question that we asked, go back to the original diagram. I'll come quickly. to the next module. Maybe before a little bit pause here. So what we have been doing, because these details are missing unfortunately. So this PMU is collecting, so remember that we are putting an extra learning engine here before dumping the network into the network, likewise dumping the data. So now the question that I was asking us, that how many PMUs should be deployed, and whether these PMUs the prunability is same as this PMU or something else. It actually intuitively this should be different, because this PMU might have been placed at a bus point where there are maybe n buses junction point, and whereas this PMU might be at a n prime junction point. So as a result, the data importance of the PMUs are different actually. As a result, my prunability should not be individual PMU dependent, but systems requirement dependent, because this is actually dealing with more critical data, maybe because this is a larger junction. Possibly this should not be pruned that much, because why? Because I am not deploying PMU everywhere. I am deploying PMU optimally in certain places, and other places we call virtually monitored. Virtually monitored means those those PMU data should be able to predict the health of the other junctions. Okay, so this task is who is best aware? PDC. PDC has the knowledge of all the data or overall the system health actually. So then the question that came to us, that is it a good idea to run this thing pruning engine at the individual PMUs, because then this is we call system unaware. The pruning should be system aware. That if I have to do system aware pruning, then one possibility is that PDC dictates that okay, you do this much, you do this much. That is one possibility. Now if the PDC dictates, why don't I incorporate that running engine at the PDC itself? So meaning that the PDC gets the data, and then it decides, depending on the importance level of the PMU location, it decides how much of prunability is affordable at one PMU versus another PMU. So we have shifted your learning engine from PMUs, individual PMUs, to the PDC. Okay, this is intuitively this is going to be beneficial actually. So this is more recent work actually. Second thing is that, which is we have not finally optimized, but we are actually working, is that given that same PDC is doing job for n PMUs, there are n PMUs in the grid, and PDC is collecting data from all those PMUs, and it is actually deciding the prunability for all these things. So does the PMU have to run that engine for individual PMUs, or can I actually do the edge computing optimization at the PDC? So we came up with a proposition that we call experience transfer, that PDC, the experience gained from the one PMU's data pruning, possibly some experience can be useful for another PMU, and as we keep on transferring, it happens that my what is called processing requirement is not simply n times individual PMU processing requirement, but it is significantly low. In one case, for one PMU I compute, for the next PMU my computation requirement is much lesser, and then as I go further and further away, it is a little bit more, but overall computation can be optimized if I utilize the experience of compressibility or prunability of the different PMUs actually. So these are certain other things. There are multiple papers that we have in that direction. I actually did not. I forgot actually to include these details. So anyway, so that is one module actually. I think we can give a small pause before I go to the next module. This is the next module, and I have actually at least 3 other modules, but let me give a pause. If there are any questions, we can. You see, I have only 13 minutes left. Okay. This is the problem. Okay, so
questions?
Yeah, so any question on that? I'll quickly move on to, I think I spend more time here because I think if the audience is tuned to this thought, next modules will be actually easier. So you get the idea. there any questions on this?
Correlation between okay. So because there are correlation between the time series, but you choose to do the data-driven optimization because you have many data. But can we also do the sparsity learning? I mean, we just pick some samples and then deliver the samples to the PDC.
Actually, so as we will go to the next module, we will see actually. So first of all, this pruning is happening on real time. So I have to decide on a data, the collected sample instantly actually. So what that means is that I have to have a learning engine which is ready to do the prediction. So learning engine is there and I got a sample. All I have to decide whether this sample is useful or not. In this case, this is I call backward compatible smart PMU. Backward compatible in the sense that there is a sampler which is anyways running in the background. What I am saying is the sampler is overdoing most of the time. I want to ensure that the overdone data is not going into the network. So for that I have to have that learning engine ready, and this is how we are doing actually. If I have that luxury of looking at the data as a whole, as a batch, and then decide what are the important components, then I can do the things that you are mentioning. I'll pick up the right ones actually. In fact, this is what we are doing in the next module actually. That is one important aspect actually. Okay.
I
yeah.
understand.
So and that actually leads to the other module that I'll come to actually. So one question actually, intuitive question would be that why is the data generated so over sample data? Why oversampling has been done? That is one question should be asked actually. Okay, so this is, in fact, this is where the gap between communication engineering and power engineering. Power engineering people have come up with this device. Again, this is my thought actually. They are not aware whether they are going to choke the network. That is one reason. Other reason is that today, if we look at today's power grid monitoring network, this is being done by optical fiber. They are saying there are plenty of bandwidth, why am I bothered about it actually? But what I am thinking, our thought process is that can we do this power grid monitoring even using wireless network? Even if it is private wireless network, still if it is wireless network, that means that my bandwidth is actually important. Even on optical fiber also it is important, right? So, but the question is that why oversampling? Oversampling is being done because I need to ensure that these very infrequent instability situation can be captured. Basically, most of the time my frequency is very stable. Okay, sometimes occasionally, maybe once in a week or so, it fluctuates sharply. So these sharp fluctuation, meaning that my signal, if I look at the sampling frequency question actually. So if I look at the signal over a week, maybe over 5 days, my maximum FM is possibly maybe 100 Hertz. But maybe if I look at 7 days, then suddenly FM becomes 1000 Hertz. So now to ensure that I am able to capture those high frequency components, I am doing oversampling most of the time just for a very small occasions to ensure that I am. So that is the intuition actually. So first of all, this kind of sampling process is actually bad process. But what we wanted to do, again for a researcher, we found that this can be optimized, and for that instead of touching the device altogether, modifying the device altogether, we thought we can actually put an extra module. That module is the learning module which can do that job. Later on we are saying learning module can be passed to the PDC because PDC anyways has to do the system aware pruning, right? So that is the other aspect actually. Yeah, any other comment or questions on this? Yeah.
That's very interesting that you show that the data or the fact from the theory assumption and the experiment is very different.
Yes.
And you use the existing equipment that developed based on that theoretical assumption.
Yes.
And then what is the impact of your result when you found that it is very different from the assumption to go back to the improvement of the equipment itself?
So in fact we are going step by step actually. So as I mentioned, in this case we are improving the equipment. In fact, I have missed to have these details. I think I'll send you modified slide to have the other details actually beyond the presentation
So
actually.
you put improvement in the existing equipment?
In the equipment itself. Okay, so that itself has become a new project now actually. Why? Actually this, so the PMU is a very costly commercial device. These are, we bought a couple of PMUs from some Canadian made PMU called VZMax. And we opened one of them and then we wanted to incorporate my module. So there are basically three layers. So one is power layer, power conditioning layer, then data processing layer, and then communication layer actually. So we felt that these are coming to one bus and another bus, and then this goes to the wireline connectivity, RJ45 connectivity that goes to the network. So we thought that the sample data that is coming to the processing bus, I will tap there and then incorporate my module and I'll work. But it does not allow me actually. System doesn't allow me. Okay, so what we are doing, system doesn't allow me, and unfortunately, this is the problem of not having R&D in the country actually. Now the company who is supplier, our supplier is a marketing agent sitting in Pune, in one part of in India. They are saying they are bound by the marketing contract that they cannot touch the equipment. Okay,
Yes.
so they cannot help us in doing research with us. So I could not do anything, and we cannot go back to the Canadian company that we have an algorithm, can we implement? So what we are doing now is that we are actually starting, we have already done that. We have done a PMU development from scratch where I have every control now actually. Now there we are going to incorporate our pruning module which will work actually. So that is going to be, we call data smart PMU now. That is one level in modification that we can do, and I already mentioned that our second version that is going to happen is that I am not going to put the learning engine at the PMU. Instead, I will do at a controller, and PMUs will be acting as dumb entities. So you see So where the learning engine is, this learning engine is doing this thing, and this learning is happening at the PMU, and the learning parameters are passed to the PDC, and PDC is doing the interpolation actually. These can be inverted actually. So learning can happen at the PDC, and PDC can pass this thing over here, and then using that same, it can decide whether to transmit or not actually. Okay, so that way, that is another variant going to happen actually. That it will be now edge compute driven actually. So my PMUs are going to be much lightweight in terms of energy processing, and PMU will remain less costly, but someone has to get some feedback, and then PMU will not transmit all the data. That is one modification. Third modification that we are going to do, this is actually to be researched, is that why do I sample actually? If I know that these samples are so redundant, then can I not do a smart sampling? In fact, that is one thing that we call smart sensing. In fact, in my fourth module possibly, we are going to talk about it actually. So here, because I do not have the, because I am not a power engineer, so I didn't want to change the power layer. I thought, okay, let power layer be as it is, and let me work on above that actually. Power layer is already deciding sampling. So, but if I have to work on the sampling optimization, then I have to actually start working on the power layer also actually. Yeah. So we are looking at that actually from that perspective. So there are multiple variants of new products that are coming actually on that.
Okay, yeah, thank you.
Yeah, so I move on to the next module. Next module has one interesting theory that we have already covered in the first module actually. I'll show you very quickly what is going on. So this is also a very interesting genesis. I was excitedly presenting my PMU outcome in a conference discussion actually. So this one person who deals with smart meters, he says that looks like your algorithm can be incorporated in smart meter. Why didn't you try? So that prunability question actually. So then we started looking at the smart meter data, smart meter work actually. So we got, after doing a literature survey, we found there is a, the database, data set available, MIT RED data set this is called, different power meter data. And using that power meter data, we started our research actually. No experiment here. We started with theory and then again we come to the experiment later. Now, what is the uniqueness here? Power meter is a gadget which is deployed, I think, in every household and everywhere today. The purpose of the smart power meter has been that they are supposed to sample the what is that called power consumption at a very high frequency. It is anywhere between 1 second and up to 30 seconds at a high frequency. And these high frequency sampled data has to be collected by the these called head-end system, and then it will be eventually going to the repository, and from the repository your billing agent will be doing billing and other people will be doing other things. Now question is that for billing agent it does not require high sampling, right? So why do I need high sampling? So high sampling, the power smart meter design idea was that if I sample this power consumption pattern at a high rate, then I am going to monitor the power consumption anyways as a byproduct, but more importantly, because I am sampling at a high rate, I can actually monitor the appliance health conditions. That is a very nice outcome actually. So there are algorithms. In fact, MIT's research was in that direction. Data disaggregation algorithm, data disaggregation actually. So if I collect my power meters data, and then if I know the individual appliances patterns of consumption, I can actually extract that, okay, out of this consumption, this much came from this much came from this, etc. And also, if let's say from the power meter data, I can find out that, okay, last 1 hour, my washing machine was running, and from that washing machine's consumption pattern, I can actually calculate whether washing machine is running in good health or not actually. That is actually a fantastic byproduct. Okay. The other thing is also this, for the power distribution people, agencies, the collecting the power consumption at a frequent intervals is going to give them a power consumption variation actually, the load variation pattern. As a result, that can be used for their what is that called power distribution, their billing patterns, not billing patterns, but the what is that called, the costing pattern actually. So the peak hours, how much cost should be assigned, and so on. So there are multiple purposes. So there is a reason for having high rate data collection. Then there is also a problem that if I do the high rate data collection, but yeah, so in this case the difference is that this is the data collector. This is the data collector, and this is the final billing management. Let's say this data collector does not collect. So here now this is not push based. This is not streaming. That earlier the device was generating a sample and instantly transmitting. We were dropping some of them. That is a different question. But here this data collector actually polls a power meter every now and then, every 15 minutes typically. So every 15 minutes it collects the batch of data that this meter might have generated actually. So that means this data collection process is now non-real time. So it categorizes that this system is now non-real time IoT device. Okay, every 15 minutes I am collecting a batch of data. So my analysis, my data analysis has become modified that I have to operate on the batch of data. So my prunability is now modified. So my what is that called? My pruning algorithm, etc. concept become different. So we could not make use of those algorithms because this is not real-time data streaming actually. So what we did, we looked at this data set, we started with RED data set, and then first task we did this, we wanted to characterize the data, so distribution. That distribution gave us a nice, very nice behavior, so very similar to I was doing, Gaussian mixer model. There is a peaky nature, and so on actually. So what we want is that I have these samples. These samples have certain distribution, empirical distribution. Now I want to decide how many what are the samples I want to transmit. As you were mentioning, one question was that you pick up which sample to be transmitted. So basically, first of all, I need to see from all these samples what is the distribution of the data. Okay. Now I come up with my algorithm, sparse sampling algorithm. Okay, that is exactly we used. We have not innovated anything here actually. We use sparse sampling technique, but this sparse sampling technique will now collect the sparsely some samples to ensure, now I have to ensure that this sparse data is not going to lose the integrity, meaning the distribution should remain as close as possible to the real empirical distribution. Okay, that is all we are talking about. So we have used this sparse sampling technique from the transmitter perspective, and from the receiver's perspective there are algorithms. We use subspace pursuit algorithm for interpolating. So the task becomes that this is my the empirical data distribution, and then as you can see, we are modeling this as a Gaussian mixture, and we are going to so here we chose a different measure, distance measure, and that distance measure is because that distance measure actually also defined something what is acceptable, what is unacceptable. Previous distance measure was a measure, but there was no useful information how much below which we cannot use actually. So anyways, so I'll here. So as you can see, empirical versus if I do Gaussian mixture. See, also earlier people tried from a different perspective, but they tried to model Gaussian, generalized Pareto, exponential, and so on, log normal. So versus for Gaussian mixture is looking to be very well fit. So what that means is that my empirical distribution can be now modeled as a 4 Gaussian mixture at the first we model at the source. Okay, so because empirical model cannot be used, from that empirical model I have to develop a mathematical approach, which is my 4 Gaussian mixture. These 4 Gaussian mixture will now be compared with the what is the sparsely communicated data, which will interpolate, estimate, and then we will recreate a distribution. Okay, so that is what we are doing actually. Okay, this is from the source side. We find that these Gaussian mixture, 4 Gaussian mixture can approximate this thing. Okay, this is the compressive sampling algorithm, and that is the other proposed. So here what we are doing is that algorithm is straightforward here. This is adaptive compressive sampling happening here. This is where this sparse sampling, and then you transmit very sporadically, and on the other side this is the output actually. So this is what is happening here. So bandwidth saving versus, so the question is that what is the batch size? In fact, when we are doing this exercise, we did not know what is the interval of data collection. We wanted to study on our own because we didn't have the clear idea of the batching thing. So we found out in this case that having a batch size more than 600 samples is not useful. So because my bandwidth saving is not helping further, improving further actually. This is my RMSE. RMSE is not, so we chose to, why? Because if I create a batch much larger, forgetting about at what rate in commercially collected, then I am actually delaying the process unnecessarily, right? I am creating larger batch means I am delaying the process unnecessarily. I can say that, okay, I don't need to go beyond that because it is not saving me any further. Bandwidth saving is improving further, but this is important actually in terms of RMSE. So going further, so basically, so this is now we compared this thing. So empirical versus at the source end 4GM versus 4GM reconstructed. So they are by visibly matching well, and these are also computed with some numbers somewhere here. So bandwidth saving, etc. So this is this technique we found it is much easily implementable, and we actually looked at. There are many other details. Again, I am skipping through. Yeah. So this is, then again same question comes. So when you started this exercise, in power meter, most critical parameter is the apparent power. Apparent power is what is used for power value computation. How much is your billing? So we started with a single variate, and that exercise gave us paper and patent. And then we wanted to implement. We wanted to do multivariate. Here again techniques are different because I have a batch. We have used the PCA for batch reduction, batch size reduction. And then after that, we have used this on the single remaining streams. We have used these adaptive compressive sampling, and then reverse processes, inverse processes happening at the receiver actually. So this, because a smart meter is much simpler device, we were able to implement that entire detail in our smart meters. We have achieved the lab level testing, and we are working on commercialization right now. Okay, so this is a kind of a institute level implementation deployments. Okay, so this is before going to this module. One question actually I'll pose here. See what we are doing in the first two cases. There were a lot of redundant data being transmitted, and we wanted to choke them, reduce them to only transmit the useful data. Okay, in both cases. Now we have actually created a problem for ourselves. What happened is that my network, which was my data which was resilient to network failure earlier because of a lot of redundancy, now because I don't have any redundancy, I am actually doing only optimal transmission, my data has become very vulnerable. So I need to actually develop some new technique to ensure that my data is sufficiently transmitted. Okay, robust actually. So basically we innovated, what is that called, we developed a research problem for ourselves actually. That we created a situation where my data is now very useful data. All data are very vulnerable data actually. So how do I protect? Now question is that if I do obliviously, if I say that okay, this much protection, so whatever bandwidth saving I was achieving at the application layer, I might lose by over protecting. I can do channel coding heavily, and I might lose all the benefits. So now can we do jointly? This that prunability and channel awareness, can this be done together? We have a paper actually, but there is a scope to improve on that actually. So this is basically a byproduct work that we have developed for ourselves. I think there is a paper somewhere. Okay, so I think again I can give a small pause, and how much time I have altogether? 16 past 10. Okay, so let me use maybe 10 minutes, and then we'll go to the other module. Okay, so now there are many details here. Actually, what I will do is network sensing. I think I'll come back a little bit later. This is the more important thing is smart sensing. This is one thing that so far. As I mentioned, I have a device already given to me. For example, we got the smart meter for our implementation, which gives me RS485 data bus through which the sample data is given to me actually. So we have applied our algorithm on top of that actually. So you got a basic transformer with RS485 output. On that we are incorporating our module, and then our communication module, rest of the things, and we have incorporated. So basically this is backward compatible in the sense that sampling is done and we are working on the prunability. So we call these as smart pruning or smart compression techniques actually, data smart meter and data smart etc. Now here, if I have the entire control of the device, I go back to a diagram maybe. So let's say this is one study we have been doing since several years, the pollution monitoring. So so far we have not actually questioned ourselves. So when I am sampling frequently, I was not worried about whether sampling itself is consuming energy or not. Okay, so if I look at these application, pollution monitoring application, so I have 10 pollutants that I have to monitor. So PM 2.5, PM10, carbon monoxide, ammonia, nitrogen oxide, nitrogen dioxide, sulfur dioxide, H2S, etc. So each parameter sampling itself is very energy consuming. So the question is that should I go by that oversampling approach and then do pruning? then what will happen is that my sampling is going to already consume a lot of energy. Then I am going to pull further, I am going to cause again some energy consumption. It is not worthwhile. So I actually need to ensure that I don't sample itself unnecessarily. So that is called smart sensing actually. So I have multiple parameters. Now again I started with a single case. Let's consider a single parameter. Now how do I decide what are the samples to be collected? So that is the one part. If I call it single variate data, where I need to what is that called? Based on my past history of data, I need to find out in the next batch, or not. I'll not call it next batch, next interval. Basically, I have a measurement cycle. In a measurement cycle, what are the samples to be collected? And based on that, as I am continuing to match with the history, with my background data and so on, I need to again for the next measurement cycle, what are the samples to be collected? So this question is here difficult, harder, because I do not have any background data to compare with, because I am only collecting the some sporadic samples. I don't have all the intermediate samples now with me to compare actually. So we used some known learning tool techniques. Many details here. So we used Gaussian process regressor and support vector, not support vector. This is called space sparse Bayesian learning technique. And for extending to multiple parameters, we used multi-arm bandit algorithm. So again, question is that if I have multiple parameters, I need to exploit the cross correlation and then temporal correlation. So these are certain things that we are doing. I'll quickly, so these modules will be helping me to explain. Okay. So this is cross correlation based sampling, meaning that I am just first exploiting the cross correlation and then deciding what are the parameters to be collected. So out of these P parameters, I might have to take care of maybe some fraction of them actually. So train the Gaussian process regressor, create the n active sets out of P using P sensors, and then find the optimal sensor set using upper confidence bound algorithm, send the information to the sensor node, and so this algorithm is sitting at the edge node, because sensor node is has to be lightweight. So this edge node is doing this task actually, and then it sends these optimal sensor set information to the sensor node, and this sensor node is collecting sample from those sensor nodes. This is being updated over every measurement cycle. Okay, so that process is being repeated actually. So this is we broke down the problem into two parts. One is that we first exploited the cross correlation here, and in next part we have exploited cross correlation and temporal correlation together, and we have a similar algorithm here. So this is what this part we have not completely implemented in hardware, but theoretically we have significant benefit we are observing actually. Okay. So this is the smart sensing, where we are exploiting the at the node level. For an individual node has multiple parameters. We call multi-sensor node. So how to optimally collect the samples actually. So that goes to take us to another module, which network sensing. This case is we did only theoretical study using data, of course. That now imagine that I have so far we are talking about temporal correlation, cross correlation. There is another correlation which is called spatial correlation. If I deploy sensors in a field, let's say two-dimensional field, normally sensors are deployed in a dense manner so that you ensure that some sensors failure can be taken care by other sensors, etc. Now the question is that at any point in time, how many sensors to be activated to create the pollution map or whatever signal variation. So we model this problem in this way, that let us consider it one-dimensional scenario, and there is a central controller which is collecting data from all these sensors potentially, and then it is trying to create the pollution map, and it is trying to compare with respect to the ground truth. There is a polluter. If this is pollution is changing with time, it is propagating as the distance progresses. So how many sensors to be activated? So this is the problem that we are talking about. And there are second module here, we broke down this into, I think I can skip that. This is from centralized to decentralized scenario, clustered based approach. And this is for single sensor. And then single sensor, we are only exploiting the spatial correlation. Exploiting the spatial correlation, and from centralized version to decentralized version. And finally, we are looking at the multi-sensing scenario. Why multi-sensing scenario is to be considered here uniquely, because different sensing parameters have different temporal and spatial correlation coefficient. So some parameters have a what is that called decay rate, temporal and spatial decay rate faster compared to the others. As a result, for different parameters, the spatial activation of the sensors have to be different. So these are all theoretical studies based on the data. You can have a look. This Vinny Gupta, who is now a faculty in US, was the primary worker student here actually. So yeah, I think these are the some outcomes. The other module I may have to skip because of time. Is maybe in 5 minutes I can explain. This problem is actually a industry given problem. Okay, this is not organically generated, but we found a very nice problem out of it actually. So industry problem is our service provider, Airtel. Airtel is Indian telecom service provider, one of them. So they came up with a problem that normally base stations are, the service providers don't maintain the base station. There is a third party, another company, who maintains the site, and they provide power, and then the telecom operator goes and deploys their equipment, and they are satisfied with as long as the power is constantly available, and they also get the monthly bill for powering. So that company, the operator came to us saying that their monthly bill is much higher than they expect, but they have no way to challenge. So they have asked us that can you monitor you develop some electronic gadget which will monitor at their secured point and tell whether the source is A, B or C. So now from the what is that called, base station provider, they are saying, okay, I am consuming diesel more, maybe as a result my consumption is higher actually. Our Indian situation is that sometimes diesel is not even poured into the bucket, they have stolen the diesel itself, and actually diesel was not run, that itself is another problem actually. So question is that goes to the problem actually. So basically they are saying that, so this is the utility. Utility could be the, let's say, service providers or operators equipment. The operator's equipment gets a minus 48 volt DC line, and source 1 could be diesel generator, source 2 could be power grid, and source 3 could be solar panel, likewise other. And these sources are one at a time connected. Okay, so when the solar panel is sufficiently generating, grid is not operating, and source 1 DG is also not operating. On the other hand, if solar source is not sufficient and solar is not sufficient, grid is not sufficient, then DG is operating, etc. So now challenge for us is that, so there is a DC power man. These all things go to through a SMPS. SMPS is the switch mode power supply actually. It goes all these the powers that are being generated potentially, they go through a SMPS, and then this minus 48 volt line goes over here actually. They are allowing us to monitor the signal over here, minus 48 volt line at the output of the SMPS. So how do we monitor how do we extract the signature of the sources? Okay, so signature of the sources, so that from there we can identify whether this is source A, B or C. So we took up this problem and we did some, so our initial intuitive thought was that the challenge is that SMPS actually, whatever signal it gets, it chops into DC-DC converter concept actually. It chops into much finer granularity at a higher frequency, and then it does its own, I don't know SMPS as such other detail, but basically the signature that these individual sources might have are getting destroyed by the SMPS's internal operation actually. So what we did, we thought, okay, we will sample at a rate even much higher than SMPS sampling rate, so that maybe certain signatures that are actually not smeared by the SMPS, maybe they are still retained, and we will collect that actually. So we planned that way actually. But we got some success, but the challenge is that this success is not, if I design this solution for one site, it does not work for another site, because the different sites have different switch modes, power supply, manufacturers are different, DG sets are different, and so on. Like company of solar also are different. As a result, their signatures are changing site to site and also time to time. Your grid signature also varies with time. In the morning time, grid power is more smooth. As the day progresses, because of these extra power the extraction, they also create harmonics and so on. So the signatures actually change. So that is where we had to rely on the learning heavily. So we are still fine tuning. This is in progress, but this is a problem from the industry, and I do not know whether we have some data. So as you can see here, that we have used some learning tools here, data-driven learning tools. We are continuing to evolve on that. Currently, this is field tested actually, our technique. So I am not going to go into many details. And this is the hardware setting. So basically we are doing more of power engineering in this task, but ultimately this is actually learning aided tool development or IoT development actually. So yeah, I think yeah, so this is the last slide actually on this, what we were looking at is that the backward compatible, if I have this slide possibly can be generalized actually for many other applications. So here I have talked about pollution monitoring as one application, which is clean slate design direction, but this is non-real time. And the other direction is that real time we talked about PMU, non-real time we talked about the smart meter, but one can actually customize. For example, in agricultural scenario, what works may not work for maybe vineyard monitoring, may not work for maybe one type of agricultural monitoring from another to another type of agricultural monitoring, and likewise medical health monitoring might require different optimization. That is one aspect. The other aspect that I actually did not discuss is that when I have clean slate design opportunity, then I can do, we call data-driven solutions, customizable RT, NRT design solution, and also data-driven dynamic priority solution. For example, if I can actually do my sensing can be actually data-driven. For example, I sense some parameters and I sense value is going to be alarming, then I have to sense possibly higher frequency. So a simple example could be ant colony actually. So yeah, on the table maybe one or two ants very lazily going around, and if I drop a cube of sugar, and suddenly in a few seconds there will be a lot of ants and their mobility becomes much agile actually. They become very quickly. So kind of we can think of that way, that when I find that some sample is alarming, I need to quickly adapt my sampling. That goes at the node level. But then my access pattern also becomes modified. I was possibly doing non-real time lazily, but when I see the data as critical, has become critical, my same node that is generating non-real time data, it has now started generating real-time data. My access algorithm has to be modified now. Likewise, routing algorithm has to be modified. So earlier I had some delay budget, so data packet has to be delivered accordingly. But now as the delay budget, let's say I have 10 millisecond delay budget. So I have to go n hops. And as I go from one hop to two hop to third hop to etc., depending on the delay budget, my priority can be modified actually. So maybe initially it was high priority, but as went faster and faster, maybe towards the end it can be low priority. Because, so these kind of things that are possible we are exploring. We have done up to the access part, but routing part there is a good scope to work as well actually. Okay, and this can be, as I mentioned, we have reasonable confidence that this can be optimized from other aspects as well. I think I will close from here at this stage. So this is kind of another this thing, yeah. So there are several students who actually I have worked with on this, Satyam, etc. Okay, so maybe we can have a small pause and then we go to the. Yeah, if there are questions.
Are there questions? Still another one talk, right?
Yeah, another talk. I hopefully will try to motivate and then close speak. Yeah, feel free to ask question because I think if there is anything interesting. Students. Yeah, yeah.
Data stream or data collecting, how maybe professor have shared something about bandwidth allocating or bandwidth management?
Could you please repeat the question?
Okay,
Sorry.
I'm curious about the bandwidth allocation because so many sensors that deploy in the network, so those affect through the workload of the system. So maybe professor has something developed to solve the increase of the data driven.
Yeah. Actually, see that. In fact, if I go back, my smart grid work actually was motivated by that because I am a network person, so I have to ensure that the network is not choked unnecessarily. So I was coming from that perspective that I don't want to generate data so that unnecessarily bandwidth will be consumed. That is how I started with. But I'll answer your question maybe from a different angle also.
Yeah. Yes.
Bandwidth. So here I am actually talking about bandwidth management in that perspective, right? I am ensuring my data generated is minimal or just barely required actually. So that automatically takes care of the bandwidth aspect.
Yeah, I was seeing from your slide that you put like scheduling after collecting data after 10 minutes. Is that right? To collect data. Is that increasing the data loading or the bandwidth?
No, so that scheduling, you see, I think in the smart meter, it collects it polling based. This is called head end control, head end system, HES. HES polls smart meter 1, then smart meter 2, smart meter 3, and smart meter N. It goes back to smart meter 1. This is a simple polling approach, round robin polling approach.
So,
Okay.
I wanted to maybe I didn't get the idea of the management of the bandwidth. If you are using like a lot of sampling of or high sampling rate, how you manage the data? Maybe you can explain in the simple way.
So you see I am sampling, let's say in same way node 1 to node n. Now earlier they were generating, let's say 10 MB at every sample I was collecting 10 MB. Now after my algorithm implementation, each of them are generating maybe 2 KB. Okay. So what is happening is that I don't need that much time again. Okay. Earlier 10 MB was taking some T unit of time to be collected. So now because each node is generating approximately only a fraction of this volume, my time required for collecting the data is going to be reduced. So my polling can be much faster now. Because earlier, what is the polling interval? Node 1 to node 2, polling interval is dependent on how much time I take to collect the node 1's data. Once I finish the node 1's data collection, then I go to poll node 2. Right? That data collection time is now reduced. So my polling distance also can be reduced correspondingly, right? So that is one way to look at. But there is also a research problem to be solved. In fact, we are working on this. So what is happening is that earlier I was having the constant data volume. Okay, I had 600 samples, and for each sample I have some, let's say 8-bit parts, this thing, your quantization and so on. So I know exact volume actually. Now here, the sample that I have, these 600 samples that I collected, out of 600 samples, I am only fraction of them are useful, constant anymore. I have reduced, but this has become a what is that called, a random. So that itself is a question: how do I optimally choose the interval between polling so that I make sure of the benefit that I have achieved here, yet I don't collide with this data collection to the next sampling. Does that make sense? This actually an additional problem actually, that my data that I am collecting, this is, I mentioned in the slide somewhere, this is called dynamic compression. A compression that is happening, or pruning that is happening, it is dynamically changing actually. Depending on the what is that called, correlation, cross correlation and temporal correlation, my compressibility actually changes. So as a result, my data volume is different. As a result, my data collection time also changes. So that is one question. Actually, we have this student actually has some work. Maybe you could have a look, Mayuk Raichaudhuri. So we have actually we looked at the access perspective, massive machine type connectivity perspective, and we actually looked at this what is that called, delay aware data collection and priority aware data collection. There are multiple variants actually. We also applied ML in that actually. So that could give some additional clue.
Okay, thank you.
Okay. Yeah. So yeah. We can go to the next module.
Next module. Okay. Wait.
So
we can take photo first together. Ayo kita ambil foto dulu sama-sama sambil break.
Okay, before the next session, maybe we should take a photo first.
yeah, maybe
Okay.
2 minutes or 5 minutes break is okay.
Okay.
Stretch their legs.
Let's take photo. Listen. Singkirin nih. Come on. Sambil mungkin agak ke sini dulu. Ini agak sini, agak melengkung gini sedikit.
Okay, thank you. Wait, let's take a break for 5 minutes.
communications or computer technology?
Maybe in engineering physics, we usually familiar with prediction, data prediction,
Okay.
like that you presented lately. And actually, I have a question, sir. I want to know that the proposed algorithm for the prediction, is it the same as like LSTM? And if it the same, what is the benefit of your proposed prediction method rather than like the existing prediction method like LSTM or convolutional neural networks and anything like that?
So we are not proposing any new method here. We are utilizing the right tool. So you see, this is what. So we are using right ML tool here actually. We are identifying first, motivating that right tool is important. In fact, we tried with LSTM, and we found LSTM is heavy. We decided that we don't want to go for LSTM. Instead, we went to this multivariate SBM, and we proposed. So you see, if you look at the paper, you will see that we are on one end we are using known learning tools. On the other end, we are also what is that called improvising by introducing new concept. For example, in the multivariate SBM, the concept of the base attribute and secondary attribute, this question we have introduced, and then we went for multivariate attribute, multivariate SBM. So there are this is how we evolved actually. Okay, and likewise for the smart sensing also, we have used known techniques like upper confidence bound, these bandit algorithms. These are all being used in the literature, but we are looking at this in this is applied research engineering, we call it actually. So in the context of pollution monitoring, in the context of multivariate sensing where temporal and cross correlation being exploited together has not been done. Spatial correlation has not been done sufficiently at all actually. So if you look at the literature. So this is how the contribution is actually. So this entire presentation is where innovation is coming by from the observation of the application actually, context. We call context aware algorithms actually.
Oh,
so observing the context, we are choosing the right direction actually.
I see.
And yeah, right.
Right.
Yeah. And as I mentioned, we are also generating our own problem. One problem was that if I have these data that I have generated which are sufficiently pruned, only useful data is being transmitted. How do I now ensure that it can handle the network vulnerability? So to do network vulnerability, I can, of course, I know a conventional approach is the channel coding. But this channel coding approach has to be done differently for real-time application, for non-real-time application. Non-real-time application, I have the luxury for retransmission if failure happens. So my overhead has to be appropriately adjusted. On the other hand, for the real-time, I don't have luxury for retransmission, so I have to do again, if you look at, we have come up with some learning techniques there, channel learning, and we correspondingly proposed. We first theoretically calculated what could be done using conventional tools. Further, if we use channel learning, then what can we do?
Okay, so thank you. Answer. Okay. Maybe we should go to the next session for the module 2.
Yep.
Okay.
Yeah. Okay, so this topic is a bit quite away from what we are discussing so far, intelligent task offloading in age-assisted surveillance. I am going to give you the overview of the problem, and there are many details which I will skip through, and this is some preliminary work we have done. And the major work are yet to be declared, yet to be published actually. So on one direction, we are looking at scenarios where bandwidth requirement is more and more. As you can see here, that as the next generation's evolutions are happening, the bandwidth requirement is larger and larger. And there are scenarios where we need to evolve techniques. Instead of simply communicating the data, we need to see if the processing can be done locally, or where the processing should be done and how much fraction of the processing should be done. These are the questions we are asking. This is battlefield scenario. Defense application is one very pertinent application actually. So spectrum, it could be because of spectrum scarcity, it could be because of spectrum is not secured enough, like defense scenario, and so on. Okay, so here, so basically, so let me see here. Yeah. So okay, so let me go to the model. This here. I'll go to the this diagram first actually. So as I mentioned, I'm not going to spend much time. So motivation here is that, so we are situational awareness is the question actually. So in a scenario, let's say in a battlefield scenario, you are taking help of certain drones, and each of them are capable to do some local information collection. Because let's say if we talk about field of view, okay, only let's say they have only camera, nothing else. Okay, so but one drone has certain field of views, it can capture certain part, another drone can collect certain part, and then these information can be eventually stitched together to create a situation awareness. Okay, that is fine. So that is our objective eventually, but we reduce the problem for our research purpose, research claim purpose. So we reduce to a single node, single UAV situation first. Let us consider a single UAV, and single UAV has been given a task that, okay, you are allowed to, you are given this track to go. Okay, along this track you collect, you go and you collect these, you sense this, and then tell us if there is any hazardous activity going on. Or okay, so now what? So the challenge that UAV has is that UAV has some limited battery capacity and limited computational capability, and also the one parameter that it can play with is that it can move faster or slower. Its mobility can be mobility speed can be adjusted, and also its what is that called? Its collection rate. For example, if I am talking about video only, so your snap rate can be adjusted from anywhere between 7.5 frames per second to 100 frames per second. Okay. So how many snaps I collect at a time, that rate can be adjusted actually. So the standard rate is that it can go from anywhere from 7.5 to 100 frames per second in the high density video context actually. So it has certain capabilities, it has certain constraints. And other constant also is that this network bandwidth that I have here, bandwidth is not reliable because of the feeding channel. Also bandwidth is not secured necessarily, and what is the alternative if it has limited capability? So question is that situation to do situational awareness, it is just only image collection is not enough. Just taking snap is not enough. That snap has to be processed. These the images that it collects, it has to be processed, and from the processed information it has to extract a kind of do the analytics, and you have to extract whether this processed information gives me any threat or not actually. Okay. So the question is that this processing can be done locally, or it can be done maybe remotely. Maybe this could be edge node, we call edge assisted actually. So now the question is that this edge node, to have the edge assistance, it has to first communicate, and then edge node will process and then send back the information. So imagine the scenario that this node decides that I collected some snaps and I don't want to process, I transmit everything to this node, and this node processes and then sends back the information, and accordingly it acts in the next moment. and this process continues. Or maybe in the next moment, this UAV decides that, okay, I will do locally processing, I will not transmit to these things, and so on. So this is where the questions are actually. So the UAV has to take decisions whether it should do local processing or remote processing, and these decisions outcome is not immediately available actually, because when it let's say it decides to compute locally, it will take some time to process because its processor is slow, it takes more time to process. On the other hand, if it has to communicate, it takes some time to communicate, that is one question, but its processor is much faster. But the question is, it has to transmit all this data actually. So it is a combination of your computation speed and energy consumption and communication bandwidth restriction. So it has to decide what to be done, whether locally or remotely, and its outcome is not immediately available actually. This is actually you can from a classical process perspective, it can be considered as a Markov decision process. So Markov decision process, but in the Markov decision process, what happens is that I take an action, and that action gives me a reward or benefit. And in the conventional Markov decision process, that reward or benefit is available instantly. In this case, this reward or benefit information is not available instantly. It is coming a delayed version. We call delayed reward actually, because when I decide to process, after a while, after processing, I found out that okay, it was not worthwhile processing locally because it was not actually critical information. Okay, so whether ultimately it has to decide between benign information or critical information. So it does not know before processing whether it is going to process benign information or critical information. So this is the question that learning, we actually use reinforcement learning in this case, and how to correct this, what is it called, continue this process. This is the overall problem actually. So I think, let me go back now. Yeah, so now if you look at here, what this is actually, I'm posing this as a research problem, and as I mentioned, this is a newly evolving direction and we are working. So UAV uploading strategies considered only communication channel constraint, and criticality of data content while making decision is also has not been considered. These are the two critical aspects actually. Whether the data criticality is not known to me, I have to make assessment about from my past history, and yet my current decision may be wrong. Okay, and that is what I am going to correct in the process of reinforcement learning actually. So what we are looking at is the energy, as I mentioned the constraints, the energy limitation, time criticality for object recognition, and the context sensitive UAV operation. So the other question I was also saying, that if the UAV finds that this information that it processed is benign, or it anticipates that the next information is going to be benign, it can actually move faster and it can reduce its snap rate, and it can go in other way if it finds criticality. And other question I mentioned, communication channel constraint and data criticality states. So here we model this as Markov decision process, and Markov decision process, because this is a dynamic, so we modified this as reinforcement learning actually. And in this scenario particularly, we are looking at this frame drop rate as the measure actually. So as I mentioned, see this, we propose a delayed reward state action, this is actually the Markov decision process. And this, because this is evolving system, it is a reinforcement learning. So this is one thing also I keep telling my students, that instead of directly jumping onto ML or machine learning tools, you first go through your basic fundamentals of basic theory. For example, without knowing Markov processes and Markov decision processes and hidden Markov processes, if you go to just use reinforcement learning tool, then you actually miss the fundamentals actually. So you cannot motivate the others that, okay, why you are using this thing. So that is we have been trying to do in this context also. And so basically we have, I quickly go into, so this is the problem, as I mentioned, there are benign, there are etc. Now we have so we model this in for our research problem formulation perspective. We model in this way actually. The channel is modeled, channel's availability or goodness or badness is modeled in this using two-step model, good or bad. Okay. Likewise, criticality, we are deciding these are two possibilities, critical or non-critical. So each of them, this is actually 2x2 matrix, and if you combine this thing, you have the 4x4 decision variables that you have, and we have to actually make a decision out of that actually. So this is what I was talking about actually. So this is the ground control station, which you can call as edge assisted edge node, which is assisting in the decision making process, and this is the UAV node actually. So this feedback comes here, and then it decides to transmit. Whenever it decides, that means it is asking this edge node to process, and that processing information is the reward is not coming instantly. Instead, it is coming after this much time actually, and at this time it might decide, okay, I will not transmit, or maybe I transmitted, it is lost, and this process continues actually. So this is the delayed reward that we are talking about. Okay, and likewise this reward also happens in this scenario. I think packet, I think in both cases actually. So as I mentioned, that these given that 2x2 matrix, we have the state space is in this form actually, critical, non-critical times good channel and bad channel. So the we need to at any point in time we need to decide based on these four possibilities actually. Is there anything I missed here? Okay. So okay, so what is the optimization goal here? We are looking at the frame drop rate has to be kept at certain minimum, and we are trying to maximize the energy remaining of the UAV. Okay, so this is a formulation. This formulation can be modified for different other contexts depending on what is your primary objective. So optimization problem determines optimal offloading policy such that energy remaining is maximized, and subject to the constant. C1 constant is fundamental constant, that energy remaining is between 0 and Emax, and then there is a delay constant. Delay constant is also subjective, whether it is the critical data, for that it has a delay constant, and for non-critical data it has a different delay constant actually. So these have to be ensured. And energy, now the energy remaining has been formulated in some way. This is in the previous step, nth step, energy remaining, if I want to compute, that depends on what was the remaining energy and whether I decide to transmit or whether I decide to process locally. Okay, these are the corresponding states. If n equal to 1, my accents, this is an accent state is 1, then I am transmitting that. Corresponding, I will have some energy consumption because I am transmitting volume data. On the other hand, if I decide to compute locally, then I have communication energy is less, but my computation energy is much more. Correspondingly, I have some remaining energy in the nth cycle actually. Okay, so then there is a benchmark that we are talking about here. The delay threshold limit has to be so. Okay, in the nth time, the number of how many non-critical frames were dropped versus what is the total delayed feedback available. That is the kind of a performance measure that we are considering here. Okay, so the reward is computed in this formula here. Total reward over n frames over video is depending on the previous rewards, corresponding weight parameters, and so these rewards are modeled as this sigmoid function in the case of these modified sigmoid function in the two cases actually. So for the remaining energy, and this is for the Rn1, Rn2 and Rn3 actually. Okay, so I think there are many details which I am not able to explain here in the sake of time. Okay, so let me see. So this is I have in eta 1, eta 2, eta 3. Basically, at any point in time, one of them is active actually, and that is why these are indicator variables, 0 and 1s. And reward or penalty for judicious use of remaining UAV energy is Rn1 is a sigmoid function, and reward functions corresponding to the critical frame drop constant and non-critical frame drop constant are corresponding. So this is about reward penalty for energy consumption, and this is about reward penalty for the frame drop. Now the reward and is different for the critical frame, and reward is different from non-critical frame. That differentiates between these Rn2 and Rn3 actually. Okay, so this is a heuristic function that is developed, which is to kind of motivate these parameters are within this. This heuristic is actually motivated by this constant here. Actually. Okay. So this is what is happening actually. So state action reward design is for different. So depending on the state, channel state, good and non-critical. If it is decided to do an equal to 1 corresponds to local processing, and so you can see certain cases we are getting reward and certain cases we are getting benefit actually. So if we look at these. Your non-critical, the nth stage non-critical delay is less than non-critical, less than corresponding threshold. So which is a good thing, because an equal to 1 corresponds to local processing. So I have decided that I'll do locally, and that is if this condition fulfills, that means I get a reward, and eta 2 is corresponding to forgetting this parameter here. Eta 2 is the indicator variable, and because this is for eta 2 is for critical, and so this goes 0, and this is eta 3 is 1, and so on. So this needs to be looked into. These parameters basically by this an. Choice of an and corresponding values of whether it is meeting the threshold or it is exceeding the threshold, the corresponding reward penalty functions are affected. So one thing that is happening here is that it has decided to process locally, and the nth the delay budget has gone beyond the delay threshold, and it gets a penalty here. This is one way to look at actually. And likewise this is the other cases actually. So this is going to give us, so this is a simple study here, that if I had considered only channel state based versus only criticality based, versus if I consider channel state and criticality together, what is the achievable gain actually. I think this is what is captured in these cases. One state you decide to transmit, 2 state is the only channel condition based, and 4 state is what we are talking about. So it shows that by accounting for channel data criticality and channel state, we have certain benefit which is residing over here actually. Okay, so which is what is that called? Percentage of frame dropped has reduced, and correspondingly, if we look at remaining energy of the UAV, and with 4 state, remaining energy of the UAV is in this case a little poorer, but this is where we are gaining significantly in terms of drop rate. Okay. So this kind of motivates the fact that by your this channel dynamics and the nodes state and nodes processing capability can be, if we factor together, then we have certain gain in terms of performance. Okay. Okay. So so the application, UAV application is power intensive. So we need to decide where to do processing, and communication consumes and also processing also consumes. So we are looking at the the optimization there. And the other question that we are looking at is that this has certain drop rate has been reduced compared to the previous approaches. And there are certain several approaches that we are currently looking at, and this is actually has been submitted. We are currently working on final generalized version. What we are looking at further in this context is that the channel model that we have used so far is classical channel model. That we are looking at if we can do data driven channel model, UAV channel model, your generative adversarial network based approach, data driven UAV localization and swarm packing. So this also helps in terms of eliminating the communication error if they are localized more accurately, and multi UAV coordination and UAV swarm aided task offloading and other situational awareness. So these are the certain things that are possible extensions, and we are currently working on the first module, primarily channel model aspects actually. Okay, so what I do is I think I can stop here, or I can give an overview of the other aspect what I was talking about if I go back a little bit with regard to the channel constant I was talking about actually. So one thing that I mentioned in one of these this diagram also, of course, motivating are here also. So the channel availability is one question, that how to optimize the channel utilization is the next module. I think I can give a pause and maybe take questions. Okay. And this kind of goes in a little bit different direction. It has its own value. Okay, spectrum sharing. Why the spectrum sharing is I have kind of overlapped with that is because I'm using the same spectrum which is sometimes vulnerable, sometimes not vulnerable, and its vulnerability could be because of the channel itself or feeding channel itself, or vulnerability could be because of the adversarial existence. So that is where we are talking about a friendly coexistence under that condition, how to achieve these goals and so on. So I think I can stop here and maybe take questions if there is anything.
Okay.
I have already extended too much.
Maybe I have a question,
Yeah,
sir.
yeah,
I have interest in reinforcement learning, and there's something that I'm still do not understand about that algorithm. Is what is the called delay reward that you presented earlier? I still don't understand in the mathematics formulation where is the delay function, or was it called delay reward like that?
Good question. I explained, possibly it was not sufficient. So I see if you go back to this diagram, this is exactly where we can quickly appreciate actually. So at this time, UAV has two choices. One is that it wants to process locally, but it could be possible that processing locally will cause certain so it after processing locally it might find that this data was not critical. Okay. Okay. And as a result it might have wasted energy unnecessarily. Okay. So that reward came after the processing, and that processing is actually sufficient time delay intensive, because this UAV is actually a slow processor. It does not have high compute capability because it is low energy, the energy constant device actually. So that is one delay, and corresponding reward or penalty is coming because after I take a decision, it turns out that decision was actually not correct decision. So, or if the decision was taken correctly, then I get reward. If decision is not correct, then I get a penalty actually. So, likewise here, if he decides that okay, I will ask this edge node to do the processing. So, edge node is given this responsibility for processing. The advantage is that it will process faster compared to the this node because it has a slower processor, but it is going to consume energy. But at the end of this thing, if faster processing is important, if the data is critical, okay, it could happen that it has decided to ask this guy to do the processing, edge compute node, but after edge compute gave feedback, it gave feedback that this was actually not critical data. So this is a wrong decision actually, and this is coming after a while. This is one because it has a processing delay which is smaller than this processing delay still, but it also has a propagation delay. So twice propagation delay. So that is the delayed reward. Okay. So this is actually important parameter actually here.
Okay, thank you, sir. Is there any questions? Maybe because of the time that we have time, maybe one more questions for this second module. Anyone?
Yeah, maybe from these guys.
Huh.
In the future direction, you mentioned about GAN. So what it will be looks like for the channel modeling.
So this is data-driven channel model, and this is we are exploring currently generative adversarial network. In fact, there are a lot of papers which are coming up already. We are trying to see what are we call PyGAN, and PyGAN we are trying to define in our own. Pi is physics aware actually, physics aware generative adversarial network. So we are trying to see what extra parameters could be introduced so that my channel as a prediction quality could be better actually. For example, maybe time of the day. So we are interested in one direction is the satellite channel model. The LEO satellite connectivity is going to be a next generation this thing. So in this case, what happens is that as the channel, the signal comes, your plasma layer thickness varies significantly depending on the day of the time actually, in the night, afternoon time, evening time, morning time, etc. So those factors, so how many factors can be incorporated? Temperature, humidity, those are the parameters we are trying to incorporate, and then trying to see if we can make our channel modeling which is closer to. Yeah, so that is one thing. This is in the exploration stage. We have some work, but I have nothing to be reported yet actually.
Okay, thank you.
Okay, sir. Okay, everyone. Let's take applause for Professor Swadesde. Thank you for the presentation and insightful thought about these two topics that have been presented earlier. Okay, right now we are proceeding to the final session. There is certificate session. So certificate of appreciation will be presented to Professor Swadesde. Thank you for your coming and for your insightful thought, and will be delivered by Professor Endra Julianto as the representative of this event. Okay. Maybe for Professor and Professor Endra can. Oke, mungkin bisa tepuk tangan. And also we have some presents from okay. Yeah. Okay. Let's take applause for Professor Swadesde for insightful thought. Okay, I think we we reached the final session, and again, I will want to say thank you for Professor Swadisde for the insightful thought that for me it's very interesting, and I want to say thank you for everyone for participating for this event. Maybe because we have tight time, I will end this event. So good afternoon, everyone, and thank you for participating. Okay.
I have a student working with but this one is we have problem in the network, urban road network, and we would like to reduce the number of the sensors, but still maintaining the traffic information and weather information. And we follow with the graph theory to reduce and to do the clustering, and then we stand it with the gun to perform the estimation. It was like I think that's actually quite similar, but you talk a lot about the bandwidth.